All right, well, yeah, I'll go ahead and start now. All right, so thanks for the opportunity to talk to this. So we are going back to the moon as a nation, as a country, as a world. And as such, going to the South Pole. The Artemis missions will have astronauts in them. These astronauts will be collecting samples. Certainly after Artemis 3, the astronauts will be collecting samples that are cold, and even Artemis 3 astronauts will be collecting samples that may have volatiles on them, right? Okay, so NASA is already thinking about preparing what needs to be done when these samples come back and how to collect them to preserve the volatiles and things of that nature. So this report is a brief out on a specific action team that was stood up by ExMAG and LEAG at the request of NASA to understand where we stand right now and where we need to be, or what we need to do to get ready for the return of cold conditioned and volatile bearing samples. So to the extent that this report you agree with, that's due to the team members. The team was fantastic. I just organized one part of it. There are actually three different I guess panels, right? And the one I'm reporting out on is volatile samples code creation. Sarah Valencia and Tim Glotch are running two other ones, and they will be done finishing up theirs later. We just turned in our rough draft on June 12th. And well, I'll get to the schedule in a second. But our charge, as you can see here, is to look at 5 different themes, and we addressed it in 5 different themes, with 2 and 3 being very similar. The first one is understanding the science. What science is obtained or retained, and what science is lost in collection, transport, and curation and study of cold conditioned, and potentially volatile-rich samples at various temperatures. All right, so very science-driven. The other 2 are what measurements and activities are needed, both in terms of characterizing the samples to pick the ones you want to pick, and also understand the science once you collect them. Right. Then the 4th theme is understanding the state of readiness for the analysis community, both in terms of people, assets, where we need to go, where we stand now, what we can leverage, and finally, what curation capabilities do we have and that are adequate, and where do we need to go to be ready for these? And there's a lot of work. So the slide doesn't have any great pictures in it. It's going to have a whole lot of words, and I try to highlight the words that really count. The takeaway I want to have here is to basically give this information out to the community so you can ask for us for the report if you otherwise didn't know about it. And to remind everybody that, these reports, they're done, and engineering decisions will be made based off these reports. And as these reports changes, engineering decision will change as well. But at some point, engineers will have to have requirements to build to. And reports like these are the ones that define those requirements for the engineers. So it's very important that we get this right. So we spent a lot of time reaching out to the community, and this report is more or less final. But if there's anything in there that's wrong, that needs to be improved, or we're missing something, then email us, let us know about it, and we'll do our best to get it back into there so that NASA gets this right and the right things are developed for us. Okay, so this is the team, Caitlin, Emily. Oh, all right, so yes, we have planetary scientists, see them up there. Also, you may not recognize Emily Seneth Smith. She was brought on because she's an expert in sampling and the science of permafrost. Right, and that's about the most similar terrain you have on the Earth compared to the Moon. It isn't really the same, but it's very useful techniques that they have developed there that we investigated for using here. I want to also point out in particular Alexander and Zoe, Executive Secretary grad students. They were absolutely essential to the successful conduction of this by keeping us organized. That was incredibly important. Also, not just taking notes, but also contributing scientifically. So shout out to including grad students in this area. And of course, the leadership that enabled this. So this was pretty quick. We kicked off in November, more or less. Took us time to, gathering community input through a variety of means, and maybe you were part of that. We reached out to the community through different forums, emails, and surveys. We presented rough drafts at LPSC, had two meetings there at this last LPSC. Limited review was sent out to certain select people for feedback, and thank you if you were one of them. Final draft was submitted, and it's currently under review. So what I'm going to do now is talk about each of the 5 themes and the findings from them just briefly. First one is science-driven, and the science drivers really are from the Artemis science document, yes, the Artemis program. And we simply attempted to understand what science is retained and lost at different temp regimes that were provided. Some were provided to us. We also selected several on our own that we thought were representative of not exactly what's technologically feasible, because we don't want to constrain ourselves by what current technology can do, but where we consider the best cut points to be. These numbers aren't written in stone at all. They can move as needed. These are just something to get us going so we make reasonable decisions. In the report, these words are replaced by a lot of details, but eye chart's useless, right? So I simply replace paragraphs with single words, and the science questions or drivers by the short words if possible. So key takeaways of this: ambient conditions, still important to maintain integrity of those samples. There's still volatile information that one can get seriously compromised, of course, but still very useful, as we saw earlier about volatile temperature, 273 Kelvin or so. OH is stable, that's volatile, plus you need to keep the sample pristine. No atmospheric gases. I'll get into this later. As you get colder, ice becomes more easy to maintain. Water becomes easier. As you get really cold, then you can start retaining the hypervolatiles. And you could start addressing these various questions from a little bit or none to fully, and from volatile composition to the sources of the volatiles, the mobility of the volatiles, to how the regolith is modified, how water may migrate and other volatiles may migrate over the surface, to the effect of human impact on the science itself. And at the lowest temperature, asterisks are down there because the preservation of the science set with hypervolatiles are very strongly linked to which hypervolatile you're talking about. Different volatiles are attained at different temperatures, so you just don't go to minus or below 123 and retain everything.
3 minutes.
Oh my goodness gracious. All right. Thank you for the heads up. So just read the headings here. All right, ambient temperatures. I already went over this pretty much, right? I just talked about this right now, just a few seconds ago. So we'll move on. The last one is tools, volatile sampling preservation. Keep those tools cold. Theme 2, activities required. Well, for measurements, basically, even these single lines are smaller than, are abbreviated from what's in the report, but I grade them out and then try to summarize everything in a bullet. Keep your, actually more measurements are better in both the number and diversity. Sampling approaches, coring is clearly the best, but all are useful, and often others in coring are much more appropriate based off the astronaut's capabilities. Theme 3, other activities to ensure that we can interpret the science correctly. Really, I'm just going to go backwards real quick if I can, right here. The measurements, contextual information before, during, after sample collection, basically like voting, vote early, vote often, and even after the polls close. So collect all the information all the time that you can, right? And finally, last finding is for other activities to mitigate contamination. That's tough. We need to figure that one out, right? That one's going to be hard. We have a lot of words in there, but it's going to be challenging. Analytical capabilities, we have great capabilities, but we need more, and the current capabilities aren't designed for cryogenic conditions and characterization. So a lot to improve there in both that, as well as, well, in order to do that, we need support, funding, facilities, and opportunities. That pretty much sums it up. This will take some support from NASA. And thank you to NASA for asking for this so that they're aware of this well ahead of time and can start building it now.
1 minute.
All right, we need to talk about how to get community readiness and outstanding challenges. Well, we have different models, labs, training, procedures, collaborations, and lessons learned. Well, there's a lot of lessons we learned from the terrestrial community. Finally, curation of it. Containment and contamination are key. Temperature, pressure, and ways to enable measurements without accessing the sample, because I tell you, when you access a sample that's cold curated, you're not going to maintain it. It's going to be exposing you to 10 to the -6 torrs. That's going to affect it. So think about ways to analyze a sample while it's actually inside the container, so you don't have to destroy it. And finally, monitoring contamination. Well, control it to the best you can and know what you've done to it. And I'll end with, finally, think long-term. Curation for tens of years, cryogenic, ultra-high vacuum, transfer the sample between different communities. That will be challenging. A lot of work, but we're getting a handle on what needs to be done. We need your input, continued input. Thank you.